These homeworks are worth, the full homework grade. So 17 is 10 points. That's 30 points. 17, 18, and 19. Any late homeworks, make sure you turn in on Thursday as well. Also, late labs, make sure you turn those in on Thursday. Chapter 17 is going to focus on acid-base, proton transfer type reactions. But there are two things in Chapter 17. One is, the prediction of the products of an acid-base reaction, and two is talking about pH. Whether the water is pH neutral, or it's acidic, or it's basic. So we'll look at those two things in this chapter. When we think about proton transfer is only of the Bronsted-Lowry type definition. We have three definitions of what an acid and base are. We have the Arrhenius definition. Arrhenius definition is a bit too narrow because Arrhenius acid is H plus AQ and Arrhenius base is OH minus AQ. And that's it. To broaden the definition of what an acid is and what a base is, we could go to Bronsted-Lowry. Bronsted-Lowry is going to be a proton donor and a proton remover, or a proton taker. It strips the proton off the acid. That's what a base is. And then we have the most comprehensive, the most general definition, which is Lewis. Lewis, in fact, we only need one definition for what an acid and base is, and that would be the Lewis. Now, the problem with Lewis is it's not as easy. If an acid or a base is a Bronsted-Lowry type acid-base, then it's much easier to treat that as a Bronsted acid-base reaction rather than a Lewis acid-base reaction, even though it's the same thing essentially. Excuse me. And so in this chapter, we're focusing on Bronsted-Lowry acid-base reactions. Now, what is a Lewis acid-base type reaction? A Lewis acid-base reaction, we could have an acid like this, BF3. BF3 is a Lewis acid, but it's not a Bronsted acid. And then when we look at BF3, there's no hydrogen here. A Bronsted acid must have hydrogen. And so here, this is our Lewis acid. NH3, this is our Lewis base. And what the Lewis base does is it donates an electron pair. So we got this lone pair, it's going to donate it to A. Now BF3 has no electron pairs, no lone pairs. Although I don't like this structure. You know what I don't like about this structure? It's missing something. What's missing? There are no lone pairs on fluorine. There should be 3 lone pairs on each fluorine. Are there any lone pairs on boron? There are no lone pairs on boron. So boron has less than an octet. So one way to make an octet is to have a Lewis acid-base reaction occur like this, and we form this. Now boron has an octet. Nitrogen still has an octet, but what's changed is formal charges. Boron will get a negative formal charge, nitrogen will get a positive formal charge. A positive formal charge on nitrogen is okay in this case. That makes that octet around similar. And so for Lewis acid-base reactions, the thing we got to look at for is we got to look at the Lewis structures and then see how the reaction occurs. This is different than a Bronsted acid-base reaction. Bronsted acid-base reaction just have a proton donor and a proton acceptor. And so here's a typical Bronsted acid-base reaction. The base is going to take the proton, the hydrogen atom from here. It's actually a hydrogen ion, H+, leave behind the electron. So the base takes the hydrogen. The charge is going to get more positive. And the acid loses that hydrogen ion, so the charge is going to get more negative. And so this is a Bronsted acid, proton transfer style reaction. And so we're going to focus on this style of reaction. some reactions. Now, this chapter is going to look at two things. It's going to look at the acidity and basicity of a solution. The acidity and basicity of a solution depends on how much acid and how much base you have in the mixture. If you have lots of acid, then it's going to be quite acidic. If you have lots of base, it's going to be quite acidic. But it depends on whether the base or the acid is strong or weak. You know, if you have lots of weak acid, it's not going to be as acidic as lots of strong acid. And so we're going to look at, you know, what causes a solution to be more acidic or more basic. This is cabbage here. The cabbage, the color of the cabbage extra